This video is on the trend of electronegativity and also a discussion of the sizes of ions. So this will pretty much wrap up our discussion of trends. So previously we've talked about atom sizes and which atom is bigger or smaller. We've talked about ionization energy and how that changes within the periodic table. And now we're going to discuss the last two, which is electronegativity and ion sizes. So electronegativity is actually a pretty simple trend. There's not a whole lot of explanation to it. So the definition of electronegativity is, the ability of an atom to attract electrons while bonded to another atom. So bonding is something that we have not discussed in great detail, although we have talked about compounds. So what we are discussing is if I have an atom bonded or connected to another atom to make a compound, we're looking at who in that compound wants the electrons more. So you'll hear me kind of say that kind of, it's not such a perfect definition, but I will always say who wants the electrons more. And that in and of itself is the idea of electronegativity. So electronegativity has a trend, and it increases as you move up in a group, and it increases as you move across the table. Okay, and so with a couple of exceptions, and that being that we actually never talk about noble gases and their electronegativity. So I'm just going to draw an X through the noble gases, and that's because if you can think back to learning about valence electrons, the noble gases have 8, they're stable, they don't want to bond with anybody. And so we kind of dismiss them from the discussion of electronegativity. So knowing that, and knowing that electronegativity increases as you move up and over, then fluorine is our most electronegative atom of all the elements. Okay, and so that means that if fluorine is bonded to anything, fluorine has a greater desire for the electron. And that's actually going to lead us to some properties that we'll discuss later. So fluorine is most electronegative, and then the element who's in the bottom left corner, who is francium, would be the least. And there's not really a big discussion of why in this case. It's just that's the only discussion we can really say is that the elements on the right-hand side of the table are the ones who would like to gain electrons. So they have a greater desire for those electrons. So that's kind of a why, but there's not really a whole lot of a discussion. So from here, you should be able to answer a question like, who is more electronegative? So if I asked you that on a quiz or something, and I gave you, let's say, carbon or oxygen. Okay, so all you have to do is think about where they are on the table. So carbon's right here and oxygen's over here. So they're in the same period. And so that means what I'm going to need to look at is where they are going this direction, right? And so since oxygen is closer to fluorine, oxygen is my more electronegative atom. So in a compound that contained carbon and oxygen. So a very famous example is CO2, right? You guys hopefully know that that's carbon dioxide. We exhale that. So in that compound, where I have a carbon and 2 oxygens, the oxygens are the ones who have a greater attraction for the electrons than the carbon. And that's all that means to be more electronegative. So that's kind of what you should be able to answer after that short discussion. That's pretty much it for electronegativity. From here, though, now we're going to switch and talk about the last trend, which is the sizes of ions. So we have to do a little bit of vocabulary refreshing here, and we have to recall what an ion is. So I basically call an ion a charged atom. And remember that occurs with a gain, or a loss of electrons. So ions, you only get an ion if the atom has gained or lost electrons, and then with that comes a charge. Okay, so we know that ions can be positive or negative. From here, we have the two more specific ions, which deal with who's the positive ion and who's the negative ion. So cations are the positive ion, and that is a result of the loss of electrons. Remember, it's kind of backwards to like what you initially think. So an example of that would be the sodium ion. Sodium loses an electron and becomes +1. So that's a cation, right? It's also an ion, but more specifically, it's a cation because it's positive. Remember my silly way to remember, right? A cation is positive. Okay, super silly, but it's the way that you can remember. So then an anion is your negative ion. That is a gain of electrons. And remember, that one's a little easier to justify only because if you think the thing is gaining, yes, but it's gaining negative electrons. So it would acquire a negative charge. So that would be like fluorine with a -1. So again, fluorine -1 is an ion, but more specifically, fluorine -1 is an anion because it is negative. Okay, so that's just a quick vocabulary review, and now we're going to talk about the sizes of these things. I'm going to do anions first. So let's do fluorine and the fluorine ion, right? So this is the atom. Oops. And this is the ion. Remember, to be an atom means to be neutral. Okay, so to talk about the sizes here, I'm going to draw pictures. So if we think about fluorine, fluorine has 9 protons in the nucleus. Okay, so I'm going to draw 2 pictures, one representing the fluorine atom and one representing F-1, which is the ion. Okay, now the fluorine atom has 9 electrons that those 9 protons are pulling on, right, or attracting. Remember when we talked about atom sizes, we did a lot of discussion about how hard the nucleus is pulling, right? And I kind of called it like pulling power of the nucleus. So that's something to keep in mind here, although we're going to venture down kind of a different road to explain why these things are different sizes. And I'll get to that in just a second. So fluorine -1 has 1 extra electron. Remember, that's a gainer. So fluorine -1 has 10 electrons instead of 9. So if you think about how hard the nucleus is pulling in each of these cases, well, the answer is actually it's pulling with the same amount of strength because they both have 9 protons. Remember, that's like the people on your tug of war team, okay? That's the pulling of the nucleus. So the answer here has to deal with something other than how hard the nucleus is pulling because they're both pulling technically with the same strength. So in this case, it has to do with how many electrons. So if you think about this example where I have 9 protons pulling on 9 electrons, and then this example where I have 9 protons pulling on 10 electrons, okay, the ion has 1 extra electron that nucleus has to work to attract. And so because of that, it's not quite able to pull those electrons quite as close as this one because this one's only got 9 electrons to pull. So that means this thing is going to be a little bit bigger than this one. Okay, so this one has more electrons, so it's going to be slightly larger. Okay, and the reason we can use that as a discussion or as a rationale is because the pulling power of the nucleus is the same. So this one has less electrons, slightly smaller. So I can make kind of a bold statement, which is that all anions, remember those are negative, are larger than their neutral parent atom. That's always going to be true. Okay, so all anions, so all negatively charged ions, will always be bigger than their neutral atom. So like sulfur -2 is larger than regular sulfur. Okay, so you might guess that cations are probably the reverse. And so here's my example. So if I compare sodium versus sodium plus 1, so it's the same rationale. Okay, if I draw my picture, here's the sodium atom, here's sodium plus 1. Sodium has 11 protons in the nucleus. And so regular sodium is pulling on 11 electrons, but sodium plus 1 has lost an electron, so it's only pulling on 10 electrons. Again, this example over here has 1 extra electron to pull, and so it's going to be a little bit larger. Okay, so it's the same reasoning here, so I can make kind of a bold statement that says all cations, are smaller than their neutral parent atom. Okay. So again, an example could be like lithium plus 1 is smaller than regular lithium. Okay, so that's how the sizes of ions compare to each other and their neutral atoms. So just one more I want to throw in here, and this is a little bit more advanced, but I think it's worth talking about. So let's talk about different ions, and this one's gonna be a little bit of a different discussion. So let's talk about sulfur -2, chlorine -1, and potassium +1. Okay, so if we were to draw these pictures, so sulfur -2, let's see, sulfur has 16 protons in the nucleus, chlorine has 17 protons in the nucleus, and potassium has 19. Remember, that number comes from the atomic number. Now, all of these things are ions, so that means that their number of electrons have changed from their number of protons, right? So S-2, it has gained 2 electrons, so instead of having 16, it has 18 electrons. Chlorine -1 has gained 1 electron, so instead of having 17, it has 18. And potassium has a +1 has lost 1 electron, so instead of having 19, it has 18. So what's interesting is that these all have 18 electrons. They have the same number of electrons. So if I were to draw my pictures, right, this time I'm talking about the protons in the nucleus pulling on the same number of electrons. So this is kind of reverse to what I just talked about up here. However, the difference, and I hope you can see it, is how many protons are in the nucleus, right? They're different. So this is where I'm going to be able to reference that idea of how hard the nucleus is pulling, because they're pulling with different amounts. So in this case, the K plus 1 is pulling the hardest, right? Why? Because it has the most protons. Okay, so if it's pulling the hardest, right, think about a tug-of-war team who's really pulling hard, that's going to be the smallest ion. So if I were to draw it, maybe it looks like this. Okay, now sulfur -2 has, it's pulling the weakest. Oops. Why? Because it has the least protons, right? And if it's not pulling very hard, then it's going to be the largest ion. So maybe it looks like this. And then what about chlorine -1? Well, that would be somewhere in the middle. So it would be bigger than this one, right? But smaller than this one. So I don't know, can I make that work? Yeah, that's not a great example, but something like that. So in terms of size here, I would have K plus being the smallest, chlorine being next in line, and sulfur -2 being the largest. And that time, we did reference how hard the nucleus was pulling because they're different ions, they have different protons, and that is going to change the explanation or the reasoning behind why these things are different sizes, because there's different numbers of protons.